Alright, this is Schweitzer. We're going to run through a video here. What we're looking at describing is enthalpy or delta H. Now, we have already kind of mentioned the words enthalpy already, but we're going to look a little closer and see kind of how it works and get some examples of it. So obviously enthalpy is kind of like heat change. So here's an example, our first one, on a heating curve. We have in this case, when you warm something up, you might do Q equals mass times change in temperature times specific heat. But when you make a transfer from a liquid to a gas, all you're doing there is breaking bonds or disrupting bonds. Okay, so here we're disrupting bonds, here we're disrupting bonds. We call this one delta H of vaporization. Energy has to get put in here, but it gets kicked out here. So this is an endothermic process. Endo, and this one is exothermic, and it's the same value. Okay, so heating and phase changes. So heat and this guy here for water, every substance is a little bit different. So a couple things you might note about this is that obviously if you have two substances that are in a solid form, let's just say hypothetically, there is going to be a relationship between the size of the delta H of fusions and the strength of the bonds between you. Obviously, the stronger the bonds here, the more is required to separate them or break them apart. So either way, at that point here, it's kind of an intermolecular forces question, and we're not super worried about that as much as we're more just kind of looking at the mathematics at this point. You'll notice also that this line is always longer, because again, you're completely breaking bonds and separating molecules, completely breaking apart bonds, as opposed to here we're kind of just disrupting them at some point. So here we go. So in this case, it is water, a solid goes to a liquid, and we get this delta H. You want to know how this relationship works here, okay? This is what they're going to call. There's never going to be anything else other than this listed here, but really what it means is kilojoules. You might see a RxN on here. What does that mean? It means every time you cycle through here and you do 1 mole of water from solid to 1 mole as a liquid, you get 6.01 kilojoules of energy. Okay, so again, that's the same thing as 18 grams. 18 grams. And this is all just proportional. So if you did 9 grams over, it would be 3.0-ish kilojoules. If you did 2 moles, it would be 12. Or if it was 36 grams, it would be 12. So there's just this linear relationship between the amount of energy exchanging hands and how much you're actually going through. So note the relationship here. So 6.01 kilojoules of energy means 1 mole of water was melted. 6.01 kilojoules of energy means 18 grams was melted. How much energy would need to melt 100 grams of ice and raise it to 10 degrees Celsius? So we want to go from here, melt it, then raise it up 10 degrees. Use the previous information from the previous video and try this problem out. Pause the video. Alright, so there are going to be 2 calculations here. One, energy needed to melt this guy. Melt. And then 2, we're going to warm it. 2 different formulas here. So one is Q equals mass times change in temperature times heat. And the other one is going to be just this 6.01. So let's do that. 100 grams. Now, there's a couple of ways you could do this. You could make up your own relationship. For example, 6.01 kilojoules per 1 mole of water. That is what that's saying. This 1 means 1 mole right here. Or it is 6.01 kilojoules per 18 grams. It's up to you. That's how much 1 mole weighs. You could do 2 steps, grams to moles. 1 mole is 18 grams. Get rid of moles and go to kilojoules. This is the delta H. 1 mole, that's this one right here, gives me 6.01 kilojoules. I'll solve out the answer here. Alright, actually, I'm assuming you can solve that out on your own. Not a big deal. This guy. Now I'm warming it. Okay, what are we doing? We're going to warm 100 grams. We're going to go from 0, because that's 0 here, to 10. So we're going to warm it 10 degrees. And then the specific heat of water is 4.18. That's a 1,000. 4,000, this would be what? 4,118. 108, I think that's what it, joules. And here, but this guy's in joules, this guy's in kilojoules. So before we do that, it'd be 4.180 kilojoules. Add the two together, and you have your answer. Total energy. Good question there. All right, next one. Take a moment and give it a try. Okay, which is true about the system provided. Now again, here we have our solid, we have our liquid, we have our gas. We got a relatively short here delta H of fusion. Here we got a relatively large delta H of vaporization. Okay. Let's see, we got this is our melting point, this is our boiling point. All right. The process is considered exothermic in W due to the fact it's getting warmer. So in W. Okay, so I guess it's not really saying here where we're going, so I'm going to have to change this a little bit and see where I mix something up here. So let's just kind of here, if we're going this way, well, if we're going from, let's put a question mark by this one. I know I'm missing something here. So we have to go from something to something. So as we move a direction, we'd have a change in temperature. There's an error in this question. The process is considered endothermic due to X not getting warmer. All right. And both processes are endothermic due to the fact that the system is gaining energy. All right. So here's the thing. Anytime we move this direction here, we are going to be adding energy into the system. Adding energy is to get warmer, adding energy system to break bonds, warmer. Everything going up is endothermic. Everything going down is going to be exothermic. We'll change up, hopefully get a better question here. I think I dropped the ball on that one. And here's the answer to the question, which wasn't there. Okay, so aluminum cans can melt down after you recycle them. So there's two parts here. One, there's same. We already did a question like this one. So pause it out and go ahead and try this problem. So aluminum cans are melted when you recycle them. If 13.5 grams of aluminum can at 20 degrees Celsius can be recycled, how much energy is required? The molar heat capacity is aluminum is 224 joules per mole per Kelvin. Okay. So now, again, you should pause this video and try this. So the first things first, I gotta warm it. 25. Again, this is like a pretty good math problem to see, okay, is it worthwhile to recycle, or is it easier just to maybe get it from a different source? So here's the melting point. So I'm gonna have to go from 1220 minus 25, because that's where I'm at currently. This guy minus that guy is what? 1190? Yeah, 1105. Okay. So a couple of things here. Again, so now that's my delta T. I'm going to go Q equals mass delta T times specific heat. Okay, they're giving me a couple of things here. That's my mass, so 13.5. Change in temperature 1195. Specific heat is telling me my molar heat of capacity is 24 joules per mole Kelvin. Now heat capacity is the same thing as this guy, so I don't have this one right here. I do have something else. I'm going to go into this way then. I'm going to say, okay, I want to go for every mole, all right, 24 joules to raise 1 mole 1 degree. And 13.5 grams is half a mole, okay? So at this point, you would want to go like this. 13.5 grams, and you get rid of grams and go to moles. 1 mole is about, for aluminum, is about 27 grams. That's half a mole. So that's 27 grams equals 0.5 moles. So it takes 24 joules to raise 1 mole 1 degree Celsius. Okay, and we're going to raise it this much. So at this point, you can say, all right, for every 1 mole, it requires 24 joules of energy. 24 joules of energy. And that tells you the energy. You could do this again a lot of ways. Let's just using proportions. So this is going to be joules per mole per degree Celsius, and then just multiply it times the number of degrees, which is going to be 1195. And let's go ahead and do that. And again, you could think of it in a lot of ways. You could think, well, you could go 24 times 1195, and that would be for 1 mole. Okay, you could do it again. I'll restate that. I did the half first, but you could go 24 joules per mole Kelvin times 1195, and that's going to give you the amount for 1 mole, the energy to warm up 1 mole. But I want half of that, so you can cut it in half. Same thing here. All right, so we got 0.5 times 24 times 1195, and I get 14,340. All right, that's 14,340 joules of energy. Okay, that's just warms it. Now I'm on my heating curve from going here, 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 here. I'm just warming it, and now I'm right here. I'm warming it to this point where I'm now going to melt it. And it says here the heat of fusion is 10.7 kilojoules per mole. Okay, so that means 0.5 moles. Get rid of mole and go to kilojoules. 1 mole is 10.7. So half of that, because I have half a mole. So 10.7 times 0.5 is just half of that, would be 5.35. Now again, once again, this is in kilojoules. 5.35 kilojoules. And then these two things you'll combine. This would then be plus 14.3 kilojoules. And I'm assuming at that point, you can add those together. All right. Another example of delta H and Q. Okay, and we want to try and start to think about what's the difference between Q and delta H. We've just done a couple problems of delta H, but what's Q? So Q is actual energy, mass times delta T times C. It's just actual energy. And delta H is the amount of energy that's given off during a process. Okay, so this would be delta H through some sort of a process. And sometimes I may make the analogy of like a bucket brigade, all right? And then the question here is, okay, the difference between Q and delta H. Delta H would be the amount of energy per every time you bring your bucket, every time you can transfer a bucket, all right? That would be like the amount of energy per, like, dumping of the fill the bucket, you dump it. Okay? So the question here says, if you're transferring this bucket, how much energy, how much water can you transfer? Well, it depends how many times you do the process. That's this. It's kilojoules or energy per reaction. Q is just kilojoules. Or I should say just joules, doesn't matter, it's energy. Okay. So sometimes I think of this process of joule as being, this guy as being joules per mole. But the mole is the number of moles that you actually cycle through the process. The process is for 1 mole. So it's kind of moles of the reaction. All right, so in this situation, let's try and come up with this on the fly. Okay, so we're going to typically do this in class. Okay, and if the NaOH is 40 grams, okay, we typically weigh out about 4 grams, which is about 1/10 of a mole. The water is collected, so now the water is our collector in this situation. It's going to collect all my energy. Before we took a beaker and we dropped a block into it, and the block radiated energy to the water. Now we got a beaker and the chemicals are going to radiate energy. So in this case, the mass of the water, let's go with 100 grams. Temperature of water like 23 degrees. And then the final temperature gets up to be usually about, let's say, 50 degrees. That's right about where it warms to. And then in this case, we have 4.18. And I want to know what is my delta H for this process. Okay. So in this situation, first thing I'm looking for is my chemical reaction here. And written out here, all I'm doing is dissolving NaOH into water, and it's quite exothermic. There are many chemical reactions in this case that are endothermic. That's how cold packs work. So when I run this thing through, what the delta H is the amount of energy for 1 mole. Okay. 1 mole of NaOH gives me this much energy, but I'm not doing 1 mole. I'm doing 4 grams. That's it. So this is going to be the Q per mole. All right. So in this case, let's find Q. Q equals mass times change in temperature times specific heat. Okay. On this thing, we want to make sure we do the whole new item here. So this, unlike the block, it's not really connected to the water. It's separate from the water. So we use the mass of the water, so change of the water, specific heat of water. Okay, so this is kind of like a new substance here. So you want to use the total mass, okay, which is just have to add the mass of the water. So this would be 104 grams. Change in temperature would be 27. And then what they do for this guy, just to make sure that they'll have a little like asterisk next to it. They'll say, oh, just so you know, the specific isn't a whole lot different than it is before. Okay, same as before. And then we get our new Q. So little difference there. Make sure you're aware of that. Let's punch it out. And then it's going to be 104 plus 27 plus 4.18 equals 135 joules of energy. Now, in this situation, 135. Now, again, these are a little bit fictional answers. We do this in class. So we get, some good numbers, I think. Although it's not perfect. So that's 135 joules. But that's going to be here, 135 joules. But that's only 135 joules for 0.1 moles. So you want to take your 4 grams. Okay, over here, 4 grams. Grams to moles. 1 mole is equal to 40 grams, which is 0.1. So 0.1, and this is just a linear proportion. So, if 4 grams got me 135, what would 40 grams get me? You can cross multiply and divide, it's the same thing. So that's going to be 13.5 joules of energy. All right. So, answer the question based off our data here. 1 mole would give me how much? Well, it would be 135. How much would 40 grams? 40, this is 1 mole. So that's 135. 4 grams is 13.5. 0.4 grams, 1.35 kilojoule. And actually, I believe we are in joules, not kilojoules. So keep that in mind. All right, next one. All right, again, I'm going to reiterate here, what is the difference between delta H and Q? Here's a pretty good analogy here. When comparing a job, the actual money your check is the Q, whereas your dollars per hour is your delta H. So it's a process. How much money do you make? Well, it depends how many hours you work. Okay, so how much energy does a reaction give off above? Okay, so the question is, for this process, well, how much energy does the reaction give off? Well, it depends how much A you push through this process. If you push 1 mole through, you're going to get 10 kilojoules energy released. Right? 2 moles, whatever. So, depends how much A goes through. 1 mole equals 10 kilojoules released. Important, important, important. 150 grams of unknown substance is dropped into 100 grams of water, and it cools from 24 to 18. The molar mass of the unknown substance is 25 grams per mole. How much energy did the water collect? What's the delta H of the process? Okay. Pause this video. You want to be trying this out. Okay. All right. So again, delta H is just Q per mole. So this process will be our first thing we're going to do. Q equals mass times change in temperature times specific heat. Okay, 150 grams of unknown substance is dropped in 100 grams of water. Now again, you know, you usually would want to do the whole thing. If it's a chemical, and like this guy is right here, okay, then we'd want to use the whole mass. And typically, okay, so let's just do the 150 plus 100. Let's do the 250 here. Change in temperature is going to go from 24 to 18 at 6 degrees. Specific heat, we'd have to have some either new specific heat given, or they'll have a stipulation that it's just pretty much like water. All right. So next up, this gives me my Q, and that's going to go up top. Okay. Now you have my moles. Okay. 150 grams. Now they're going to give you this right here. 150 grams, dot line, get rid of grams, go to moles. They could have given you a formula. 1 mole is 25 grams, divide it out. Looks like 6. And this number 6, divide out. And this would give you, now this important piece here, this gives me my joules, okay? This would be joules per mole. That's the amount of energy it takes if I put 1 mole through of this thing. What if your formula happens to be this? 2x goes to y plus energy. You know, like it's exothermic or whatever. It doesn't matter where the energy is located. When you divide out, you're automatically going to get for 1 mole. This number, if you're going to use it for this process, my delta H would have to be times 2, because that's to put 1 mole through. This guy would be for 1 mole of X. Let me rewrite it here. It'd be 1 X goes to 1/2 Y. So this delta H would be for the 1 mole. All right, but I want to put 2 moles through. This is the same process here. And you should note your delta H is different. Okay, so how is your delta H varying from these? And let's take a quick second. Sure, it'll show up later and we'll see it again. But just so you know in those two things there, that how would those two things differ? In this reaction, I have 1x goes to 1/2 y, my delta H, and I have 2x goes to y, my delta H. How are they different? You got to think about what this actually means. Okay, it's Q per mole that I'm running through. So this would be Q to run for 1 mole of X. Okay, so I'll get Q to run this thing here. Okay, if it's 10, now I'm running 2 times that. I'm running two moles through. This is 1 mole. This is 2 moles. So I'm running twice as much stuff through, so it should be 20. Okay. So just keep that in mind and have a good understanding of how Q versus K and Q versus delta H, okay? And I believe that is the end of our little discussion. Thank you very much. 24 minutes, long enough.